Hello, and welcome to Boring History for Sleep. Tonight, we drift gently through the unexamined corridors of American residential architecture, focusing on a truly understated, yet profoundly impactful aspect of our daily lives. Have you ever considered the precise, almost imperceptible thickness of the glass panes in your windows? The subtle difference between one pane and another, perhaps measured in fractions of an inch, seems inconsequential. Yet, for nearly 7 decades, from the dawn of the 20th century to its twilight in 1970, this seemingly minor detail became the subject of extensive industrial effort, meticulous engineering, and quiet, persistent standardization, shaping the very homes we inhabit without most of us ever noticing. To truly understand its quiet, pervasive influence, we must delve into the intricate beginnings of residential window glass pane thicknesses. The story of residential window glass pane thicknesses in American housing, particularly between the years 1900 and 1970, is not one filled with dramatic innovation or groundbreaking discoveries, but rather a tale of gradual refinement, industrial consensus, and the subtle, persistent push towards uniformity. Before the advent of mechanized production methods, glass manufacturing was an artisanal endeavor, a craft passed down through generations. Early window glass, prior to the 20th century, displayed a remarkable degree of variation. Depending on the method of production, whether it was crown glass, broadsheet, or early hand-blown cylinder glass, the thickness of individual panes could differ significantly, not just from one batch to another, but even within a single pane. Crown glass, for instance, involved spinning a gather of molten glass on a pontil rod, creating a large circular disc. Sections were then cut from this disc. The glass would be thickest at the center, near the pontil mark, and gradually thinner towards the edges. This inherent variability meant that architects and builders of the 18th and 19th centuries had to contend with a degree of inconsistency that would be unthinkable by the mid-20th century. Broadsheet glass, while offering larger individual panes, still suffered from waves and varying thickness due to the method of blowing a large cylinder, slitting it, and then flattening it. These historical realities set the stage for the deep-seated desire for consistency that would characterize the glass industry in the decades to follow. The turn of the 20th century marked a pivotal shift in glass production, with the introduction of mechanical drawing processes. These innovations fundamentally transformed the industry, moving it from skilled handcraft to automated, continuous manufacturing. This transition was not instantaneous, nor was it without its challenges, but it laid the groundwork for the standardization of window glass pane thicknesses. The two primary mechanical drawing methods that emerged were the Forecourt process and the Libby-Owens-Colburn process. Each brought its own set of advantages and challenges, and together they would largely define the quality and consistency of residential window glass for decades. The Forecourt process, invented in Belgium by Émile Forecourt and patented in 1904, was one of the earliest successful methods for drawing flat glass continuously and vertically directly from a tank of molten glass. Imagine a large rectangular vat, a melter, filled with liquid glass, maintained at extremely high temperatures. At one end, a ceramic block with a precisely shaped slot, known as a débetuce, was submerged just below the surface of the molten glass. As the débetuce was slowly raised, a continuous ribbon of glass was drawn vertically upwards. Much like pulling taffy, rollers positioned above the tank gripped the sides of this ribbon, steadily pulling it upward. As the glass ascended, it gradually cooled and solidified. The speed at which the glass was drawn, combined with the temperature of the molten glass and the precise dimensions of the débetuce, directly influenced the final thickness of the pane. The Forecourt process represented a remarkable leap forward. It enabled the production of glass in much longer, more uniform ribbons than ever before possible. This meant fewer optical distortions, fewer imperfections, and, critically, a more consistent thickness across the length and width of the glass sheet. However, even with this mechanical marvel, perfect consistency was an elusive goal. Minor fluctuations in glass temperature, subtle vibrations in the machinery, or infinitesimal changes in drawing speed could still lead to variations. But these variations were significantly smaller and more manageable than those inherent in older manual methods. Shortly after the forecourt process began to gain traction, the Libby-Owens process, also known as the Colburn process, emerged in the United States. Patented by Irving W. Colburn in 1902 and subsequently developed by the Libby-Owens Sheet Glass Company, which would later merge to become Libby-Owens Ford, or LF, this method offered a different approach to continuous flat glass drawing. Instead of drawing the glass vertically, the Colburn process drew it horizontally. Molten glass flowed over a lip from the melting tank, forming a sheet that was then gently bent over a large water-cooled ceramic roller, known as a bending roll. From there, the glass ribbon continued horizontally, supported by a series of smaller rollers, gradually cooling and solidifying as it progressed through a long annealing layer. The Colburn process offered several advantages. The horizontal draw often resulted in slightly better surface quality, as there was less tendency for the glass to sag under its own weight before solidifying, a minor issue that could sometimes affect vertical drawing. It also provided a more stable platform for the glass as it cooled, potentially leading to even greater consistency in thickness. Like the forecourt method, the thickness of the glass in the Colburn process was meticulously controlled by the speed of the draw, the rate of flow from the tank, and the temperature profile along the layer. By the 1910s and 1920s, both the forecourt and Colburn processes were being widely adopted in American glass factories, revolutionizing the production of window glass, or sheet glass, for residential applications. This era marked the effective end of widespread, significant thickness variation within individual panes. The challenge then became one of standardizing the categories of thickness. Builders, architects, and manufacturers needed a common language, a consistent set of expectations for what constituted a standard window pane. This need led to the informal, then increasingly formal, establishment of single-strength SS and double-strength DS glass. These terms, single-strength and double-strength, did not originate from precise engineering calculations of breaking point, but rather emerged from the practical realities of early 20th century glass manufacturing and building practices. They referred to distinct, nominal thickness categories that became widely accepted benchmarks. Single-strength glass was generally understood to have a nominal thickness of approximately 3/30ths of an inch, or about 2.5 millimeters. Double-strength glass, as its name implied, was thicker, typically around 1/8 of an inch, or roughly 3.2 millimeters. The selection of these specific thicknesses was not arbitrary. They represented a balance of several critical factors. For single-strength glass, the 3/32 thickness provided sufficient rigidity for most residential window applications of moderate size, offered adequate resistance to typical wind loads, and was economical to produce. It struck a balance between material cost, ease of handling, and acceptable performance for the vast majority of homes being built. Double-strength glass, at 1/8 inch, offered enhanced durability. It was less prone to breakage during transportation, installation, or from minor impacts, and it could accommodate larger window openings or areas subjected to higher wind pressures without excessive deflection. The slight increase in thickness also offered marginally better insulation and sound dampening, though these were not primary drivers for its initial adoption. As these categories solidified, the glass industry, comprising major players like Pittsburgh Plate Glass, PPG, Libby-Owens Ford, LOF, and American Window Glass, began to establish internal specifications for the acceptable tolerances around these nominal thicknesses. While a pane might be nominally 3/30ths inch, there was an understood range, perhaps plus or minus a few hundredths of an inch, within which the glass was still considered single strength. These tolerances were crucial for manufacturing efficiency. Aiming for absolute, perfect thickness would have been prohibitively expensive and technically challenging. Instead, the focus was on achieving a high degree of uniformity within an acceptable range. The Roaring Twenties saw a significant boom in housing construction across the United States, further accelerating the need for standardized building materials, including window glass. Architects and contractors increasingly specified SS or DS glass, trusting that the material they received from various suppliers would conform to these established thickness parameters. This period also witnessed the growing influence of industry associations and nascent standardization bodies. Organizations like the National Association of Plate Glass Manufacturers, though primarily focused on plate glass, its influence extended to broader glass discussions. And, more importantly, the American Society for Testing and Materials, ASTM, began to play a role in formalizing these industry practices. ASTM, founded in 1898, was dedicated to developing and publishing voluntary consensus standards for materials, products, systems, and services. While comprehensive, specific ASTM standards solely defining residential window glass pane thicknesses for SS and DS didn't necessarily appear overnight in their fully codified form. Instead, the process was more iterative. Industry best practices, manufacturers' specifications, and widespread acceptance of the nominal 3/32" and 1/8" thicknesses for SS and DS respectively gradually formed a de facto standard. ASTM's role was often to formalize these existing practices, providing a framework for testing and quality assurance that ensured manufacturers adhered to these common understandings. This meant that when a builder ordered single-strength glass, they could be reasonably confident that the thickness would fall within the accepted range, regardless of the specific manufacturer. The economic downturn of the Great Depression in the 1930s temporarily slowed housing construction, but it paradoxically reinforced the value of standardization. In an era of scarcity and cost consciousness, manufacturers and builders alike sought efficiencies wherever possible. Standardized glass panes meant reduced waste, simplified inventory management, and predictable material costs. It also made repairs and replacements easier, as a standard SS pane could be sourced from multiple suppliers. The meticulous control over production, now with several decades of accumulated experience with the Forecourt and Colburn processes, continued to refine thickness consistency. Engineers and factory managers continually sought ways to minimize variations, improve annealing processes to reduce internal stresses, and enhance the overall optical quality of the glass. World War II, in the 1940s, brought its own set of challenges, including material shortages and redirection of industrial capacity towards the war effort. However, the existing infrastructure for producing standardized window glass proved resilient. The need for efficient resource allocation and predictable material supply for both military and essential civilian construction reinforced the practicality of established thickness standards. The experience gained during the war, particularly in optimizing manufacturing processes under stringent conditions, would indirectly contribute to even greater precision in the post-war era. The period immediately following World War II, from the late 1940s through the 1950s, witnessed an unprecedented housing boom in the United States. Millions of homes were constructed to accommodate returning veterans and growing families, giving rise to sprawling suburbs. This explosion in residential construction placed enormous demands on the building materials industry, and glass manufacturers rose to the occasion. The standardization of single-strength and double-strength glass panes became absolutely foundational to this mass production effort. Imagine the logistical nightmare if every pane of glass varied significantly in thickness. Builders would constantly face issues with fitting glass into pre-manufactured sashes, leading to delays, increased labor costs, and higher rates of breakage. Instead, with SS and DS as established norms, window manufacturers could design and build sashes with precise rabbets, the grooves that hold the glass, that reliably accommodated the standard thicknesses. Lumberyards and building material suppliers could stock vast quantities of glass in standard sizes and thicknesses, knowing they would be interchangeable and meet the needs of diverse construction projects. This predictability was crucial for the efficiency and affordability of post-war housing. Throughout these decades, the precision of glass drawing machines continued to improve. The Forecourt and Colburn processes, while conceptually similar to their early 20th century counterparts, had undergone continuous engineering refinements. Furnaces became more efficient, temperature controls more exact, and drawing mechanisms more stable. These incremental improvements directly translated into tighter tolerances for both single-strength and double-strength glass. Manufacturers could consistently produce glass closer to the nominal 330 kef inch and 1/8 inch targets, with fewer outliers and less internal stress, leading to a higher quality product overall. The quality control methods also evolved. Visual inspection remained critical for detecting obvious flaws like bubbles, seeds, or scratches, but more precise methods for verifying thickness were integrated into the production lines. Micrometers and optical gauges were used to take precise measurements, often automatically, ensuring that the glass met the specified thickness ranges. This rigorous quality assurance was not just about meeting a standard. It was about preventing costly errors and maintaining a brand's reputation for reliability. It is important to remember that during this entire period, from 1900 to 1970, the vast majority of residential window glass in the United States was still what was broadly termed sheet glass, or window glass, produced by these drawing methods. Plate glass, which offered superior optical clarity due to a grinding and polishing process, was significantly more expensive and primarily reserved for large commercial storefronts, high-end architectural applications, or automotive windshields. Plate glass also had its own thickness standards, generally starting thicker than DS glass, but it was not the everyday window material for residential housing. The late 1950s brought a truly revolutionary development in the flat glass industry, the float glass process, invented by Sir Alastair Pilkington in 1959. This method involved floating a continuous ribbon of molten glass over a bath of molten tin. The glass, being lighter than tin, spread out evenly, and the perfectly flat, liquid surface of the tin imparted an incredibly smooth, parallel, and distortion-free surface to the glass. The thickness of the glass was controlled by the speed at which it was pulled from the tin bath. The beauty of the float process was its inherent ability to produce glass with unparalleled flatness, parallelism, and, crucially for our topic, exceptional consistency in thickness. However, it is vital to contextualize the impact of float glass within our specific timeframe of 1900 to 1970, and for residential window pane thicknesses. While float glass was invented in 1959, its widespread adoption and displacement of drawn sheet glass for standard residential windows did not happen overnight. The initial capital investment for float glass plants was enormous, and it took time for the technology to be licensed and implemented globally. Early float glass production primarily focused on replacing plate glass for high-quality applications where optical clarity was paramount. For the more cost-sensitive residential window market, drawn sheet glass continued to dominate well into the 1970s. Existing infrastructure, established supply chains, and the sufficient quality and cost-effectiveness of SS and DS drawn glass meant that the transition was gradual. Therefore, within our period, the standardization of residential window glass pane thicknesses remained largely anchored in the capabilities and evolution of the Fourcault and Colburn sheet glass drawing processes. By the 1960s, the terms single strength and double strength were so deeply ingrained in the American building lexicon that they were almost taken for granted. They were specified in architectural drawings, included in material lists, and understood implicitly by every builder, glazier, and window manufacturer. Single-strength glass remained the standard for smaller windows, particularly those in older or more modest homes, or in less exposed locations. Double-strength glass became increasingly prevalent, especially for larger window openings, in areas prone to higher winds, or in homes where a slightly more robust construction was desired. The visual difference between a 332-inch pane and a 1/8-inch pane, while subtle, could be discerned by a trained eye or felt by hand, but for most homeowners, the distinction was simply about performance and durability, not an aesthetic feature. Towards the end of our period, the late 1960s, a new concern began to emerge that would subtly influence the conversation around glass: energy efficiency. While single-pane windows, whether SS or DS, offered very limited thermal insulation, the concept of double-glazed windows, or insulated glazing units, IGUs, began to gain some traction. These units consisted of two panes of glass separated by a sealed airspace designed to improve thermal performance. Crucially, even these early IGUs relied on the established standards for individual panes. The glass components within an IGU would typically be standard single-strength or double-strength panes, simply assembled into a more complex unit. Thus, the quiet standardization of SS and DS panes provided the fundamental building blocks for future innovations in window technology. Let us delve deeper into the nuanced engineering behind these thickness standards. The primary material for glass, silica sand, when combined with soda ash, sodium carbonate, to lower the melting point, and limestone, calcium carbonate, to improve durability, formed the basic composition of soda-lime glass. The precise ratios of these raw materials influence the glass's viscosity, its working temperature range, and its ultimate strength characteristics. Maintaining a perfectly consistent melt in the furnace was a monumental task, involving precise control over fuel mixture, airflow, and raw material feed rates. Any fluctuations here could subtly alter the glass's properties, making consistent drawing more challenging. The drawing process itself was a dance of forces. In the forecourt process, the upward pull exerted by the rollers had to be perfectly balanced with the viscous resistance of the molten glass and the gravitational force. If the pull was too fast, the glass would stretch thinner; too slow, and it would thicken. The cooling rate as the glass ascended was also critical. If cooled too quickly, internal stresses could develop, making the glass brittle. If too slowly, the glass might deform under its own weight before solidifying. The annealing layer, a long, temperature-controlled tunnel, was essential for gradually cooling the glass, allowing these internal stresses to relax, resulting in a stronger, more stable product. Similarly, in the Colburn process, the precise curvature of the bending roll and the speed at which the glass flowed over it were meticulously calibrated. The horizontal support rollers had to be perfectly aligned and rotate at precisely the same speed as the glass ribbon to prevent surface imperfections or thickness variations. The annealing layer for the Colburn process was also critical, gradually bringing the glass from its molten state to room temperature without inducing stress. The nominal thicknesses of 3/32 inch and 1/8 inch were not arbitrary choices, but rather practical target ranges that the drawing machines could reliably achieve within an acceptable economic framework. Pushing for significantly thinner glass would have resulted in an unacceptably high rate of breakage during production, transport, and installation. Extremely thick glass, while stronger, would have been heavier, more expensive, and reduced light transmission. Besides requiring larger, heavier sashes and frames, the chosen thicknesses represented a sweet spot for general residential construction. The tolerances around these nominal thicknesses were also a subject of continuous refinement. Early in the century, a single-strength pane might have varied by several hundredths of an inch. By 1970, the manufacturing processes had tightened these tolerances considerably. A manufacturer's specification might state, for example, that single-strength glass, nominal 2.5 mm or 0.098 inches, would have an actual thickness ranging from 2.3 mm to 2.7 mm. These seemingly tiny differences were significant from a manufacturing perspective, impacting material usage, machine calibration, and final product quality. From the architectural and construction perspective, standardized thickness was a blessing of quiet efficiency. An architect designing a home could specify single-strength window glass for a typical 24 by 30 inch window opening without needing to worry about sourcing issues or fitment problems. The sash manufacturer would then produce sashes with a precisely routed rabbet, knowing that any standard single-strength pane would fit snugly, allowing for appropriate glazing compounds or sealants. This seamless interchangeability eliminated a layer of complexity and potential error that characterized earlier building practices. Consider the economics of this standardization. For glass manufacturers, producing to consistent thickness standards simplified their production lines. They could optimize their machines for these specific thicknesses, reducing setup times and increasing output. For distributors and suppliers, it meant simplified inventory. Instead of stocking a bewildering array of subtly different thicknesses, they could categorize by SS and DS, streamlining their warehouses and order fulfillment. For builders, it meant predictability in material costs and reduced labor time, as glaziers could quickly and easily install standardized panes without custom fitting each piece. The quiet nature of this history is perhaps its most fascinating aspect. There were no public debates or grand pronouncements about the precise millimeter difference between one type of glass and another. This was an industrial evolution, driven by engineers in factories, committees in industry associations, and the pragmatic needs of the construction market. The beneficiaries were millions of homeowners, living in houses with windows that performed predictably, remained stable in their frames, and could be easily repaired or replaced when necessary, all thanks to these unheralded thickness standards. The impact of wind load on window glass selection, while a complex engineering topic, also played a role in the distinction between SS and DS. Building codes, which gradually became more prevalent and prescriptive throughout the 20th century, began to include provisions for minimum glass thicknesses based on window size, height above ground, and anticipated wind pressures in specific geographical zones. While a detailed discussion of wind load calculations is beyond our soothing scope, it's sufficient to understand that larger panes or windows in exposed locations often required the greater stiffness and strength of double-strength glass to prevent excessive deflection or catastrophic breakage under design wind loads. This practical requirement further solidified the dual standard of SS and DS. The subtle visual characteristics of SS and DS glass also contributed to their differentiation. While both were produced as window glass, sheet glass, which inherently possessed minor optical distortions, often referred to as waves or draw lines, compared to the perfectly flat plate or float glass, the increased thickness of DS glass could sometimes make these distortions slightly less noticeable or contribute to a sense of greater solidity. However, for most residential applications, the primary concern was clarity, not perfect optical flatness, and both SS and DS were considered perfectly acceptable for everyday viewing. The legacy of this quiet standardization extends far beyond 1970. Even as float glass eventually took over as the dominant production method for all flat glass, replacing drawn sheet glass for residential windows in the decades that followed, the established nominal thicknesses of 3/32 inch, or its metric equivalent of 2.5 mm, and 1/8 inch, 3.2 mm, persisted. Float glass could produce perfectly consistent glass at these exact thicknesses, making the transition seamless from a builder's and homeowner's perspective. The standard was so deeply ingrained that the new technology simply adapted to meet the existing proven benchmarks. The story of residential window glass pane thicknesses from 1900 to 1970 is therefore a testament to the power of incremental progress, industrial cooperation, and the pursuit of practical efficiency. It is a tale not of revolutionary invention, but of meticulous refinement of existing technologies. It showcases how seemingly mundane details, when consistently applied across an entire industry, can create a bedrock of reliability and predictability that underpins the comfort and functionality of millions of homes. The next time you gaze through a window, perhaps you'll quietly appreciate the millimeters and fractions of an inch that were painstakingly standardized over 7 decades, allowing that pane of glass to quietly fulfill its purpose, standing steadfastly against the elements, a silent sentinel of comfort in the American home. And with that thought, may you drift into a peaceful and deep sleep.